Ladies and gentlemen, hello and welcome to our first KEMET webinar in 2020 on our KEMET automotive current sensors for DC charging applications. My name is Alexander Nebel and I will moderate the webinar today. We are very pleased that you find the time to join our webinar. Presenter today is Michael Freitag, our product manager for magnetics. Before we start our webinar, I have some information for you. We invite you to ask us questions. You can address your questions at any time during the webinar with the chat function on the right-hand side in your browser. We will answer all of your questions at the end of the webinar. Also, no need to take notes. We will publish the presentation afterwards. Hello Michael, thank you for presenting today. Please tell the audience shortly about your role inside KEMET and then you can directly start your presentation.
Hi Alex, hello and good afternoon to everyone. I am Michael Freitag. I'm responsible for the magnetic sensor and actuator business group in Europe as in product management. And I'm happy to have the webinar today. So we actually had a little bit of problems of audio connection, but this is now solved as far as you can hear me. And as Alex said, I will start right now. So today is probably a rather short webinar because it's only or mainly about one product that we are going to launch, or we actually have launched this already, and this will become available with the first pieces of production now in February 2020. And as you can see on the screen, it's a current sensor for DC charging applications, which is a little bit specific, and probably the ones that dialed in today have exactly expected this kind of announcement that we're doing today, but we also talk a little bit about the roadmap further on and where this sensor is required and what are the standards behind which need to be satisfied. So let's have a look in DC charging applications, and by the way, we call this DC charging applications because at the end, as you see on the far right side, the final stage for all these electrical vehicle charging is always DC. Whether it is DC from the beginning when you plug it in your car, or whether it's still AC and will be converted by an onboard charger. And as you can see on the screen, I mean, I've divided this into these two sections. Actually, one is exactly the AC to AC charging, where you find a lot of applications today already, either as a wall box or as a, let's say, power connector cable, where the little bit of control is built into the cable, which is usually then supplied when you buy a plug-in hybrid electrical car or a very small electric car. And then the AC is provided to an onboard charger. The onboard charger that usually sits in every electric or plug-in electric vehicle, and it is kind of the converter which converts the AC into DC. In the lower section, there's basically a pure DC charger, which is already on the network side and the grid side converting to DC voltages, and this usually can be found for quick charging stations with higher output power and higher output currents, because every onboard charger, of course, has its limit from the power level that it can convert. And if you want to charge a car quicker, then you need to supply DC in the right voltage level that you basically can fill up the battery pack on the far right-hand side. So there's obviously some differences, and but all of those require AC and DC leakage current sensing. I think one of those, I mean, before, I mean, it was last year when it was not really by a standard required, but actually I think either this January or last year January, there was a switch, and then there should be DC leakage also in addition to AC leakage detected, and also there are limits now set. Of course, as these standards are or these applications are pretty new and also handling a lot of energy. There were some, let's say, governmental standards, European standards established, and as well, of course, in the United States or in Americas in general, and also in Asia. So that is why still standards are changing. I wouldn't say frequently, but it's kind of everything is in the first place, let's say, where it's really established. So when we divide this, I mean, you have seen on the overview that there's AC to AC and AC to DC charging. If there are some different modes, let's say, applicable, which are satisfied by a certain IEC standard, where I come further to. There's the basic or the lowest level mode is mode 2, and this is applicable for chargers which are really built into the cable. And I have kind of closed out a little bit the other areas. I focused here on the European market, but however, this is of course similar. And then for when it comes to wall boxes, when you have really a charging station, then there is a mode 3, and mode 3 is divided into various, let's say, power levels. So, so this is then starting when you have a wall box which has a fixed connection to grid, or if it's even a higher power AC output where this KC might be applicable. And then, of course, for DC charging, we have mode 4, and you can see also from the plug, the lower 2 connectors are made for like the DC connection to the car that you can usually more quickly charge an electrical vehicle. So these are the basic, the 3 different modes, mode 2, mode 3, mode 4. And then when it comes to the requirements of these different charging modes and the leakage detection requirements, you can see some differences, but also there are some similarities. I mean, if we look at the different modes in the table here, IEC 62752, which is mode 2, then you can see that the DC level where the leakage needs to be detected is in both cases 6 milliamps, but the AC level is different. And also the break times vary, things like this. But in general, it's the same concept. Mode 3, as you can see, is in total or in maximum going to up to 125 amps, where mode 2 is only up to 32 amps. So that's one of the power level differences. But however, I mean, these modes are relatively similar, but when it comes to impulse withstanding voltage, break times, and also the individual allowed levels, these are a little bit different, right, from each other. So what needs to be known is that mode 1 is not allowed in Europe anymore. But mode 2 is basically the entry level for these cable-mounted chargers. Mode 3, as I said, for wall boxes or everything what is fixed mount. And mode 4, then for the DC level kind of things. So how is the detection being done? I mean, when you look at the principle, and I mean, there's various possibilities how to detect leakage currents. But our aim was to create a sensor which can detect AC leakage as well as DC leakage, because when you have, and you know this probably, when you have a house or a flat, an apartment, then basically you have an AC leakage switch or detector, usually in your switchboard. But when there's like a DC leakage, then you would probably not get aware of, and as we're talking about high voltage, which is probably coming then in an error case from the car, which could be 400 volts or something, of course, it needs to be protected that people will have no possibility to also be applied to these kind of high voltage DC levels. When there's basically an AC leakage, then you have usually the the 50 hertz or 60 hertz, whatever your supply frequency is, which is detected by the coil. I mean, usually when these how many conductors you have through the magnetic core doesn't really matter. Usually, when you have all of those which are supplying the application, then the zero phase current should be zero. So there should be no leakage, because everything what current goes in should go out as well as usual. If you have one phase and one neutral, or if you have three phases and one neutral, it doesn't matter. The tricky thing is how to detect DC leakages, and there's, as I said, there's a bunch of different possibilities to do this. We are doing this in that way that basically when there's a DC overlaid in a coil, it will change basically from the oscillator the duty cycle, and so that means that, for instance, usually when there's no leakage, you have like 50% duty cycle, means 50% on, 50% off time, and when there is a current, a leakage current in DC, then the pulse time will change and will increase. So that means it could go up to, for instance, 60% of duty cycle, where you have the on time and only 40% the off time. So that is the basic principle. And how do we do this? So these the measurements are related, of course, to the primary current, and every magnetic material has some kind of influence when you overlay a DC current. So that means that you that you shift across the x-axis by the electric current. So it means you change the behavior of the VH curve, and so with the oscillator we can then define this in kind of a duty cycle. If it's 50-50, there's no leakage. If it's varying, then we have either a minus or a positive leakage in this case. And an AC leakage, of course, can be detected because it's visible through the supply frequency in the secondary coil, and that is the more easy way to detect these things. So in general, and here you can see we have three conductors, but as I said, it's not really limited to. I mean, the current sensor is designed actually for three phases maximum and one neutral. But I mean, in general, it would work in many other cases as well. It comes, when you look at the layout principle, with analog and with logic in and output. So an analog output tells you exactly what kind of leakage is there that can be estimated. I mean, if you're not at zero, but shifting a little bit around the lower milliamps, then the power electronics can already foresee that there might be, especially when it becomes wet outside or something like this, that the level could increase in this case, or there is something. However, this will not trigger an alarm. The alarms are clearly identified, and they are digital signals for AC and DC alarms. And we also have a logic or digital input for a test. I mean, you know this probably also from your switchboard. When you have an AC leakage detector, you have a button usually which you can push, and then basically it creates a leakage that, let's say mechanically or electrically, or by pushing the button. And at the end, it will show if the device would work properly and if it really cuts off basically the electric energy, right? This is how it looks like. And then there's, of course, as you have seen maybe on the table, there were some different kind of reaction times, let's say, to cut off a certain leakage current. In this case, I mean, typically when there's leakage of DC of 4.5 milliamps, then it will detect. So that means the DC digital alarm signal will go on a high level, and it recovers once it's half of this current. So that means of this typical current. So in this case, 2.25 milliamps, and then it would reset the alarm. You can see on the low side in the left corner, you can see the digital signals with a high signal, basically, that identify the DC alarm. Same concept on the AC leakage current. The typical value is 17.5. I think on the next slide I show a table where the min and the max is. In this case, it's like 15 to 20 milliamps when it starts to react. And these AC leakage current detection complies with not only the IEC 62752, but also there is a UL norm or UL standard, the 2231 or CCID 20, which is also applicable or confirmed with this sensor to be capable with. The Mode 2 sensor that we have currently available is just the first step. We are planning to do more in this case because this is a new application area, as I said at the beginning. And in this case, we really focused on making it very easy to adapt. We have a single part number at the moment, the 12.6 millimeter hole, and the maximum which would fit through that is 4 times 10 square millimeters from the cabling. The pin assignment are rather easy. I mean, we have pin 1 assigned to the supply voltage, which is 5 volt DC plus minus 5%. 2 is ground. 3 is an analog output with a resolution of 50 volts per amp with a 2.25 volt offset in this case. Then we have the DC alarm active from minimum 3 to maximum 6 milliamps. Let's say in worst case, an AC is active from 15 to 20 milliamps, and then there's the test signal input on pin 6, which starts the test, let's say, procedure when the pulse is longer than 120 microseconds as an input. A little bit more about parameters. I don't go into every detail, but here you also can see in the middle of the screen DC fault response times and AC fault response times. The AC clearly 100% adapts the IEC and the UL standard, and the DC level in this case adapts also the IEC standard for electric charging of electrical vehicles. And basically what you can see here as well is the ambient temperature requirement, or let's say where it's working, it's from minus 40 to 85 degrees C, which should support most of the applications which are around. In this case, even if it's hot on the board, but usually, I mean, our expectation it's not more than 65 degrees C on the board level, including all the heat rises of components and in general the ambient temperature there. So it should be satisfied. So conclusion of the FGR 053 is easy to apply to measure the leakage requirements by this Mode 2. Digital alarms, output, test input integrated, analog output for other purposes, whatever you need in the charging electronics, small footprint. I mean, this is of course one of the major benefits, and a single side attachment. Accurate linear output versus ambient temperature. I mean, I haven't put this here into the presentation, but we made some investigations about the ambient temperature, and it's really, it's very, very stable and linear. It's not changing basically the alarms, whatever ambient temperature in the range from minus 40 to 85 degrees C are around. And then what we are planning, and this is what I mean with the last sentence here, upgrade compatible to Mode 3. So, I mean, this is, as I said, the first sensor we are doing, and we are planning a bunch of sensors more in that area because we see the customer requirements already coming in. So the next step, at the moment, the temporary, the Mode 3 leakage detection, I mean, I haven't seen at least a sensor on the market who can do this, will be mandatory from January 2022, as far as we know about it. And so that means in the meantime, designs could be made with a Mode 2 sensor, and this could be used until end of 2021. Now we have seen that also a lot of automotive customers producing onboard chargers requested us if we can do an automotive version, and we said, okay, that's an relatively easy fix. So we will come out later this year with an automotive qualified version. And then through the next 2 years, almost 2 years, until Mode 3 really becomes mandatory, we will upgrade the sensor to become available in like the same fit, form, and function as this sensor you see in front of you, the FG-R053, to be used in Mode 3 applications. But we want to limit this up to 3 times 32 amps. Similar to the Mode 2 is concluding. The reason is that we see most of the applications looking for 22 kilowatt maximum power, at least when you look at the, let's say, private households or apartments. There is simply not that much more energy available, and therefore we said, okay, that is basically where we are looking for. And additionally, of course, if there is a specialized requirement, I mean, we have seen different layouts mechanically of the sensors, I mean, upright, like the one we are introducing now, or even if it's like a more flat situation that you can put in the board, we can talk about this, of course. I mean, if there are demands there, we are open to listen. And we can basically, once we have now this basic kind of design, we can do this in all kind of mechanical ways that would be suitable for customers or what customers are looking for, if, of course, the demand is high enough that it satisfies the special development. But it's usually only like special plastic casing and everything else, what is inside, that we can probably keep. So it's not a real big development, but I mean, I would forecast like something like 6 to 9 months before such a production can go live in these kinds of circumstances. Then, of course, there are other current sensing requirements, and I mean, as I said, the private charging stations in neighborhoods require high electric energy, and whenever these houses were built, this was, of course, not expected. I mean, because hybrid or electrical vehicles were simply not around, and there was no demand for so much energy to take. So it could be when you have especially a high power charger that the house would be overloaded and one of the main fuses would blow up, which certainly should be avoided. And this can also happen if the electricity in the house is not, the load is not in a symmetric way. So that means in Germany we have most of the cases 3-phase attachments at each house or apartment. That might be different in Europe. I mean, especially in Southern Europe, there's usually 1-phase things where, of course, the symmetry plays no role. But specifically in Germany, I mean, symmetric load that don't need to be achieved. It depends on the electrician who has kind of done everything together, and also depends on which applications you switch on, like washing machines and tumble dryers and God knows what, which can change the symmetry. However, we have seen requests and applications going on that the charging stations are evaluating the overall power consumption of the house by phase, and is then kind of steering or controlling the charging to certain limits. So that means that whenever there is very close that probably the fuse would blow up, then the charging power would be reduced, and basically the fuses would stay in place. It just would charge the car a little bit slower. For that reason, we have some time ago released the first part of the CICT series, which is a simple AC current transformer, and it is open, as you can see on the picture, where you don't have to loosen the cables of the main power supply of the house. You can simply wrap this around like an amp meter, and then basically can use it to detect the overall current that the house is currently using, including the charging power, of course, by charging an electrical vehicle. Now we have released another type for up to, let's say, 30 amps, but 50 amps could be still measured. The old one, which we have released a couple of years ago, is for a maximum of 120 amps, and 150 amps could be still evaluated. So it's within the signal range, and it's basically for AC currents only. But this is no big issue because all the supply happening is in 50 hertz in Europe and 60 hertz in America. So that should not be an issue in this case. So this is what we can do in addition, and you can see there's a plug attached to this, but we can also, of course, change this and provide this with a different cable set. For instance, to attach this not to let's say a female connector, but probably also to an onboard connector or something. So that is something where we are also a little bit flexible in this. The output characteristics of this, caused by the magnetic material we're using, is very stable over linear, over a wide range. And for each kind of current sensor, AC current sensor that I'm talking about here, there is basically a relation between the load resistance, which you would say shortcut, let's say the output, or cross over the output. That depends on how much signal, how much output voltage you would generate at a certain current which is flowing. And of course, it's different from the 03 or 6, which is like the 30 amp sensor, to the 12 or 6, which is basically the 120 amp sensor in this case. Right? From this case. Okay, this is just in addition what we do, and then we don't have a really huge range of current sensors, but we have a few series. And if you have the demand for other AC current sensing, could it be the AC, the rated current, or it could also be another leakage current sensing that you're looking for? We have a few series or few types which can deal with this, and basically have the ability to have also like the graph I showed before, a very linear behavior. So that means that you don't need to trim your electronics that much to follow a certain curve. I mean, it's very linear over the working area range. Okay, and as I just said before, it was a rather short webinar that was today, because it's only about especially one product and a few ones that I wanted to highlight a little bit more. Alex, any questions, or how do we conclude this?
Yeah, Michael, so it was not short, it was exactly 30 minutes, so standard time.
Okay.
I received 3 questions. The first question I can answer directly was, do you send us the presentation? Yes, we will publish the presentation, and you will get the link to download this presentation afterwards. So please be patient. I guess in the next days we will send this to you. And now, Michael, 2 questions for you. The first question, will the sensor be able to use in other applications than EV charging?
Yeah, of course, no trouble. I mean, we had one case, actually, one application requirement from a customer who wanted to use it in a different kind of, call it battery management system or such, for DC. That is no trouble. I mean, it could be used basically in any other application as well, as long as the isolation voltage capability is satisfied, and as long as it does not exceed the current that I mentioned here within the webinar.
Okay. And the last question up to now is, are the current sensors available as samples?
Yeah, I personally have a few samples here at home. And then, I mean, we're at the moment establishing the part number in the system. A few weeks later, they will probably be available through all our high service distribution partners. I mean, they got already the what we call these the package for establishing those. I mean, of course, at the moment I only have still the data sheet, which is in a preliminary mode. But I mean, from I think it was the 20th of February, so probably in like 2 or 3 weeks, we have this fully available. But if you need samples before, just let us know, and let's get it to my attention, because I'm already able to ship samples out for customers which are interested in the sensor.
Okay, this was perfect, interesting information. And now this is the end of the presentation, and if there's anyone who has still some questions, you can contact Michael Freitag or your local sales contact at any time, not only for samples, also for more technical details if needed, and we will provide you with any information you need. And this seems to be the end.
Okay, perfect.
Michael, thank you for presenting today. It was quite interesting, a new product. I'm always open to see this. And yes, thank you to all attendees for joining today, and hope to see you soon again.
Yeah, thanks to you all as well, and have a great day.
Okay, goodbye.
Goodbye.